Our only question for homework over the weekend was worksheet number 7, question number 7. We had to add 4 vectors together. Now, if we had 4 vectors that were like this, we could add those together easily, right? We could have added those together easily in elementary school. If we had 4 vectors like this, we could have added those vectors together, again, fairly easily as well. It wasn't elementary school that we learned to add those together, sometime in junior high school, but in the end, it's not that hard. We just make some of them positive, some of them negative, right? But if we have 4 vectors like we have in question number 7 here, it becomes a little bit more difficult. If I'm finding the total distance traveled in this question, in other words, if I'm adding scalars together, it's still easy. We're just going to say 8 plus 12 is 20, plus 10 is 30, plus 4 is 34. If I'm adding the distances together, adding scalars, I'm going to get 34 meters, easy. But if I'm adding the vectors together, or the displacements, then I've got to deal with components, vector components. Okay, if I draw a little x, y here, tell me which one is x and which one is y. Which one's this, x or y? This is x, this is y. All right, so knowing that that's x, knowing that that's y, I've got to take each of those vectors that I have in question number 7 and identify how much of that vector is x and how much of that vector is y. So let's do that now. How much of that 8 meters is x component? How much of that is, I should have left that little grid up there. How much of that 8 meters is this one right here? 0. Yeah, it's going straight down. None of it is right or left. All of it is up or down. So we're going to say 0 is the x component. What about the second vector there? How much of that 12 meters is x component? What is it? 12. All of it, right? All of it is x component. Now, if we have one that has this angle of 30 degrees or something like that, it becomes a little bit more complicated, right? That's what we're going to deal with in a few minutes. But for now, it's either all or none. Okay, for the first one, we had none of it was x component. For the second one, we had all of it was x component. What about the third one, the 10 meters? How much of that one is x? Ernesto, how much of that 10 meters is left or right? No? 10 up, yeah. So 10 up means that we have 10 for the y component, but how much is for the x component? How much is this way? 0, right. And what about that 4 meters? How much of that 4 meters, Tyra, how much of that 4 meters is x component? Good. It's important to get that negative in there as well, right? -4. And why is it -4, Tyra, as opposed to just 4? Good, because it's going to the left. So let's add these up now. We're going to get the total x component, and then we're going to turn around and get the total y component. 0 plus 12 plus 0 plus -4 gives me 8 meters. All right, let's do the y component now. How much of that 8 meters, Daniel, how much of that 8 meters is the y component, the up and down? 8 meters, yeah, except that we're going to make it negative because it's down, right? So we're going to say -8 meters as opposed to just 8 meters. How much of that 12 meters, how much of that 12 meters is x component? Jason? Sorry, y component, I mean. I said x, I think. 0 is y component. Good. Because it's all the x component. Good. How much of that 10 meters is y component? How much of that 10 meters is y component here, Gabe? All of it, 10 meters. And it's positive because it's going up. And finally, how much of that 4 meters is x component? Nate, how much of that 4 meters is x component? Sorry, it's y component, I meant. Yeah, you're right. I said it wrong. You're right. It's 0 is y component. Okay, I said x component, which is -4, but we're supposed to be doing the y component right now. Add these up. -8 plus 10, that's it, gives me 2 meters. So there's my total y component. Now I've got to combine these. I'm going to redraw this. By the way, that original vector diagram, that's drawn correctly, right? It's not one that we can just solve right away because it's not a right angle triangle, but it is drawn correctly in the sense that we have head matching up with tail, head to tail, head to tail, head to tail, right? That resultant vector would be drawn from start to finish, from start to finish. Well, if we redraw it head to tail, then we should get a resultant vector that looks pretty much the same. We have 8 meters. How did I know it was 8 meters to the right? How did I know it wasn't to the left? Yeah, because it's positive. And then we have 2 meters that's up. How did I know that's 2 meters up as opposed to 2 meters down? Because it's positive, right? And my resultant vector, by the way, that's drawn head to tail, right? Head to tail. My resultant vector is going to be drawn start to finish, just like my resultant vector is up there. And lo and behold, the 2 resultant vectors look the same. If I draw it to the same scale, then they should look exactly the same as each other. We're going to call the resultant vector R. Where are we going to label theta? Position 1, position 2, or position 3? Position 1, 2, or 3, Josh? Position 1, good. And we're going to draw to position 1 because that's the start of my vector diagram. Where it's tail and tail, that's the start of my diagram. That's where I label my angle. Okay, how do we find the value of R? Dexter, how do we find the value of R? The value of R, not tangent. Good. It's a Pythagorean squared, right? The Pythagorean theorem, right? A squared plus B squared is equal to C squared, or C would be the square root of A squared plus B squared, or R, in this case, would be the square root of A squared plus B squared. When I do that, when I do say the square root of A squared plus B squared, I end up getting a value of 8.2 meters. But that's not enough, because that doesn't include direction. So now I have to find the angle. And Dexter, I know you're going to have to find the angle because you just told me a minute ago. What am I going to use to find the angle? Yeah, I'm going to use the tangent function because I've got opposite to the triangle, I've got adjacent to the triangle, and tangent goes with opposite and adjacent. If I'm solving for theta, I'll say that theta is the inverse tan of opposite over adjacent. Let's pull out the calculator to do this one here. Let's say second function tan. Everybody actually just, a good idea, beginning of class, every time you go to do an angle calculation for the first time, just hit sine 90. Just double check you're in degree mode. If sine 90 is equal to 1, you're in degree mode. You're good to go. Okay, we checked that, we're good to go. Now let's say second function tan, 2 over 8, and then let's close that bracket. Second function tan, or inverse tan, of 2 over 8, close the bracket. We get an angle here of 14 degrees. Now, we got to express that 14 degrees something of something. Well, this is the east, and this is the north. I'm going north, and I'm going east, right, with that resultant vector. I'm going north, and I'm going east. But am I going north of east, or am I going east of north? How many people say option 1, north of east? Okay, option 2, east of north. The angle is measured from the east, right? It's touching the east. This angle right here is touching the east. So it's from the east, or of the east. But yet I'm going north from the east. So we're going to call this north from east, or north of east. So you're correct. When you guys said that it was 14 degrees north of east, that's correct. Now, we showed you this the other day, but I'm going to show you again now that you're a little bit more comfortable with this. I could have, instead of drawing it 8 then 2, I could have drawn it 2 then 8. That's drawn head to tail still, right? Like if I said add 1 plus 2, you'd say, if we were adding scalars, you'd say you get 3, right? If I said add 2 plus 1, you'd say, well, it's 3. Doesn't matter what order we add them in. Doesn't matter what order we add these in either. 8 plus 2 is 8.2 at 14 degrees north of east. 2 plus 8 should give me the same answer. If I solve for r, it sure enough works out to be 8.2 meters. But theta would actually, if I did the inverse tan function, would actually work out to be 76 degrees. But it wouldn't be 76 degrees north of east. It would be 76 degrees. Yep. What's this for? Well, just showing you another way of drawing it, right? I had 8 and 2. So the first time I drew 8 to the right, 2 up. This time I drew 2 up and 8 to the right. You don't need to do both. I'm just showing you that if you did it the other way, we'd end up with the same answer. It would look a little bit different. Instead of 8.2, 14 degrees north of east, it would be 8.2 at 76 degrees east of north. But that's the same thing. That's like saying, you know, where is Mackenzie right now? She's 3 meters from the front of the room, or she's 5 meters from the back of the room. Like, they sound like two completely different answers, right? 3 meters from the front, 5 meters from the back, but they both describe perfectly where she is, right? So 76 degrees east of north sounds completely different than 14 degrees north of east, but really it's the same thing. It's just two different ways of expressing the same place, right? That make sense? Okay, I'm going to draw one of these for you guys to work on yourselves, and then we're going to start taking a look at these ones with the angles that aren't 90 degrees, the funny angles, as we call them here. So let me just draw one real quickly for you. Let's make this 10 meters. Let's make this 5 meters. Let's make this 5 meters, 2 meters. And let's make this 12 meters. I want you to find the resultant vector here. Listen to the ways that I could ask you the same question. Find the resultant vector. Add these vectors together. Find the total displacement. Those all mean exactly the same thing, okay? Add these vectors together. Find the resultant vector. Find the total displacement. All exactly the same thing. So let's see what we can do with that over the next couple minutes now. All right. Let's identify, just as we did with the last one, now that you finished this, the x components and the y components. And I know that some of you skipped a couple steps here. That's not the end of the world for a question like this, but know that the structure that we're using for this question is going to carry through to the questions involving angles, where in those cases, we can't skip those steps. We're not going to be able to get away with it. So we're going to go through all the steps here. Even if you did skip steps, we're going to go through all the steps because they're going to be required for the next problem that we do here. All right. How much of that 10 meters, that first vector, is x component? Colby, how much of that 10 meters is x component? Good. How much of that 5 meters is x component, Enrique? 5 meters. We're going to make it -5 though, right? Because it's going to the left. Make sense? Okay. How much of that, the next one, that 5 meters, is x component? Chloe, how much of that next 5 meters is x component? Good. How much of that 2 meters is x component? Aiden, how much of that 2 meters is x component? This one right here? What is it? Good. Not just 2. Okay, you're correct. It's -2 because it's going to the left, right? And finally, the x component of that last one is just 0, right? It's the 12 meters is straight downward. So we add these up. 0 plus -5 plus 0 plus -2 plus 0 gives me -7.0 meters. Now, I know that some of you kind of just did that in your head. And like I said, that's okay. But when we go to do the next question that involves angles, you're not going to be able to just do that in your head. So we want to get in the habit of writing it out like this, even though in a question like this we don't really need to. Okay, y components. Y components. What's the y component of that first vector? The y component of that first vector, that 10 meters. Yep. It is -10. Good. Not 10, but -10 because it's going downwards. So 10 down. Riley, what's the y component of the second one, that 5 meters? Good. What's the y component of the third one? What's the y component of the third one? Gabe, what's the y component of that 5 meters right here? Yes, good. +5 meters because it's 5 meters up, right? The y component, Daniel, of the fourth one, the 2 meters? Good. And Mason, what's the y component of the last one, the 12 meters? Good, -12. So we're going to add these up. -10 plus 0 plus 5 plus -12 gives me -17, I think, isn't it? Is that what you guys got? -17. So we got -7 meters, and we have -17 meters. So now we're going to combine these as a right angle triangle. By the way, my resultant vector in the first diagram would look like this. We just couldn't solve it directly because we didn't have a right angle triangle. My new diagram is going to have the same resultant vector, but it's going to be a nice right angle triangle, so we're going to be able to solve it fairly easily. We're going to say 7 over, and we're going to say 17 down. That resultant vector goes from start to finish. Now for my other vectors, my solid line vectors here are going head to tail. My resultant vector is drawn from start to finish. Take a look at that resultant vector. Is it not the same as the first one? As long as I draw it to the same scale, it should look exactly the same as the first one. Where am I going to label theta? Position 1, 2, or 3? Position 3, good. Now, I always get this question from people, always get this question from people, like, how do you know where to draw the angle? I say, well, always draw it at the beginning. And then you say, well, how do you know where the beginning is? Because sometimes people, this is what people do sometimes. They draw 7 meters, they draw 17 meters, and then they draw the hypotenuse like this. Well, how do you know where the beginning is in this diagram? You don't. That's why you need to draw the directions. That's why you need to draw the little arrows on the vectors. 7 meters to the left, 17 meters down. If you don't draw those arrows, then you don't know where the angle should be. Position 1, 2, or 3. All right, so let's find the value of r here. We're going to find the value of r by doing the Pythagorean theorem, right? A squared plus b squared is equal to c squared, or r is equal to the square root of 7 squared plus 17 squared. What do we end up getting for that? 18.4? Okay, we're going to round that actually to 2 digits, so we'll say it's 18 meters. 2 digits because that's what I have in my original problem, right? And then theta is the inverse tan function of opposite over adjacent. What's the opposite side, 7 or 17? Enrique, did you have a question? Sorry? Okay, go ahead. Yep. Oh, good. Like right here, positive 7 is opposed to negative 7? Well, when you're doing the Pythagorean theorem, you don't actually put the signs in. Okay? You're finding a magnitude there. So in the end, if you put negative 7 and squared negative 7, you'd get positive 49. So it doesn't really matter, but I'm just going to suggest that you leave off the negative there, okay? Okay, theta is equal to the inverse tan. What's the opposite side here, 7 or 17? 7 or 17? This is the angle. This is touching the angle, so it's got to be adjacent. This 17 has got to be the opposite side. Yeah?
So also you can drop the signs.
Yeah, you would, yeah. Although when you're doing inverse tan, if you don't drop the signs, it's not going to be a huge deal because you'll still get the same magnitude of angle, but I would, yeah. So the inverse tan, second function tan of 17 divided by 7 gives me a value of 68 degrees. Now we're going to say that's 68 degrees, what of what? North of west, south of, I'm going south and I'm going west, right? So what is it, Josh? Right, because it's measured from the west, but yet I'm going south from the west. So we're going to say 68 degrees south of west. Make sense? Is that good? All right. How is this question different than the one that we just did? What makes this one different, Josh? No, yeah, exactly. Well, we don't even have a triangle there, right? Because we have 3 vectors. And even in that last question, we didn't start off with a right angle triangle. Even in that last question, we started off with 1, 2, 3, 4, 5 vectors, right? So that wasn't a right angle triangle either. But at least all the angles were right angles. So it wasn't very hard to get a right angle triangle from that, right? In this question that we're looking at right now, we actually have less vectors. We only have 3 vectors and then the resultant vector, but they're not all right angles. We've got a 30-degree angle there. I call an angle that is not 0 or 90, I call it a funny angle. So 30 degrees is a funny angle. 20 degrees is a funny angle. 89 degrees is a funny angle. And you know what? I don't like funny angles. 5-word phrase that you're going to remember for the next 2 years of physics. I don't like funny angles. As soon as you see an angle of 30 degrees or any other angle other than 0 or 90, you're going to automatically, for the next 2 years of physics, you're going to automatically think in your head 5 words. I don't like funny angles. Got it? Repeat after me. I don't like funny angles. I don't like funny angles. Okay, good. So what do you do with it? Let's get rid of it then if we don't like it. Let's get rid of it so that we never have to see that funny angle again. Now, we've done this. We just haven't done it in the context of a question like this. Yeah, I showed you the other day how to get rid of funny angles. You just may not have been realizing that you were getting rid of the funny angles. So watch this carefully. Okay, watch what I'm about to do and see if it kind of ties in now with some of the stuff that I showed you the other day. I'm going to take this 15 meters. By the way, is this vector diagram drawn correctly? Head to tail, head to tail? It is. Head to tail, and then the resultant vector is drawn from start to finish, right? So that's good. We have a 10 meters, that's fine. I don't mind that 10 meters because that's straight across. I don't mind that 5 meters, that's fine because that's straight across. It's the 15 meters that I don't like here. It's the 15 meters that I don't like because that's at a funny angle of 30 degrees. And I don't like funny angles. So I'm going to take this 15 meters kind of off to the side over here and redraw it. I'm going to draw it like this with a little triangle around the angle. Remember what we did here a few days ago last week? We wanted to find the x and the y components of a vector that was at a funny angle. That's exactly what we're going to do right now. We're going to make this x and this y. How are we going to find the x component? Well, which side of that triangle is the hypotenuse? That 15 meters is the hypotenuse, right? The x side is what? Opposite or adjacent? Adjacent, right. It's the adjacent side. So if you have an adjacent side that is x, and you already have a hypotenuse, which trig function goes with adjacent and hypotenuse? Cosine. So let's say cosine 30 degrees is equal to adjacent over hypotenuse, or x is equal to 15 cos 30. And 15 cos 30 on our calculators is 12.99. So how much of that 15 meters is x component? 12.99. How much of its y component? Well, we're going to use the sine function for that, because the y component is the opposite side. We have the hypotenuse of 15. 15 sine 30 gives me 7.5. Now, what I do every single time I do one of these is just box that off. And the reason I do that is just to kind of set that off to the side. A couple reasons. One, I don't like funny angles. I don't want it to be with the rest of my question. I want it to be off to the side because I don't like it. Just put it in its own little place. And the second reason I do that is because it reminds me that this is the only part of the question. What I just did is the only part of this question that makes this different than that last question that we did. Now the question is exactly the same. Now the question is exactly the same as that last question you just did. Now, you could, if you wanted to, you don't have to do this, but you could, if you wanted to, erase that and redraw it. Redraw it like this: 12.99 meters this way and 7.5 meters this way. See what I just did there? I replaced a 15 meters at a funny angle that I don't like of 30 degrees with a 12.99 meters to the right and a 7.5 meters up. Now, when I do that, doesn't this question look like the one we just did? Like it looks identical to the one we just did, right? Go ahead, Josh. Yeah, because that's exactly it. Yes, I got rid of the 15 meters because I already solved for the x and y components of it. Once I do this little thing off to the side right here, once I do this little thing, x and y components in the box off to the side, that 15 meters is dead to me. I never want to see that 15 meters again. Okay, it's gone out of my life forever. So if I want to, I can scratch it out or erase it like I just did, right? And then I use the 12.99, right, and the 7.5. So what you're doing here is saying, I don't like that 15 meters at 30 degrees. I'd rather use 12.99 and 7.5 than the 15 meters. So that's what I'm going to do. What's the x component of the first one? How much of that 10 meters? How much of that 10 meters is x component? 10 meters. What's the x component of the second one, that 5 meters? 0. Yeah, 0. Now, see how many of you get this one. What's the x component of the third one, that dead to us 15 meters? 12.99, right? 12.99. Add these up, and we get a total x component of 22.99 meters. Now, the y component of the first one is what? 0. What's the y component of the second one? What is it? Negative 5 meters. Kira, what's the y component of the third one? Good. It's not 15. That's gone. Like, we're never going to use that again. Never. It's 7.5, and it is positive because it's up, right? We add these up. 0 plus negative 5 plus 7.5 gives me positive 2.5 meters. What do you think I'm going to do with this now? Now that I have the total x and the total y, what do you think I'm going to do with it? Redraw it. Yeah, redraw it. I got 22.99 to the right. And I have 2.5 up. Right, 22.99 to the right because it's positive, 2.5 up because it's positive as well. I could have drawn them the other way around. I could have drawn 2.5, then 22.99. That would have been fine, as long as they're both drawn head to tail. The resultant vector is drawn from start to finish. And if I draw it to the same scale, lo and behold, it looks like the resultant vector that I have in my first diagram. It's just easier to find now because I got a right angle triangle. So we can do this. R is equal to the square root of 22.99 squared plus 2.5 squared. R is going to work out to be, let's do this as a group here, okay? Let's say second function square root 22.99 squared. Even if it was negative, we drop the negative at this point. Plus 2.5 squared, and the bracket. I get 23. To 2 digits, I get 23 meters. But that's not enough. I need a direction. Where am I going to label the angle? Position 1, position 2, or position 3? Where is it, Ernesto? Good. Because that's the start of my diagram, right? So I'm going to say theta is equal to the inverse tan of opposite over adjacent, 2.5 over 22.99. Do you expect a big number here or a small number? Yeah, it should be pretty small. I'm not sure exactly what, but let's say inverse tan. If this is the first time we're doing an angle calculation for the day, let's do sine 90 first, just to make sure that we're in the right mode, right? But we've already done it, so we're good. The inverse tan of 2.5 over 22.99 gives us 6.2 degrees. The 2 digits. Now, how do we express that? 6.2, what of what? We're going north and we're going east, right? My angle is measured from the east, so we're going to call it north from east or north of east, right? North from east. or north of east. Does that make sense? What makes this question different than the one you did for homework over the weekend and then the one that we did in class a few minutes ago? What's the stuff that's boxed off to the side there, right? Getting rid of that funny angle. You're going to get a question in a few moments. You're going to have a break here. But then after the break, you're going to come back and you're going to work on a couple questions where we have one, sometimes two, sometimes three funny angles. If you had three funny angles, you just make three boxes off to the side, like we did here. Does that make sense? See a funny angle? I don't like funny angles. You see two funny angles? I don't like funny angles times two. Okay, you don't like funny angles? All right, deal with them. Get rid of them, turn it into X and Y, and then just do what we do. We're going to have you guys work on 3 questions now for the next little while. On your worksheet number 7, questions 8, 9, and 10. Now notice in question 8, there's one funny angle, 30 degrees. So I'm not going to do this for you, but I'm just going to remind you what you're going to do with that, right? I don't like funny angles, so I'm going to take that one funny angle off to the side, and I'm going to break it into X and Y. Now, over here, in question number 9, I've also got one 30-degree angle. Now notice in question number 9, some people will get mixed up here and say, oh, that 75 meters is relevant to the 50. It is not. These are 3 separate vectors. The 50 meters is right here, and there's an X component and there's a Y component that have nothing to do with that 75. They're independent of one another. So just get rid of the 30 degrees, 50 meters at 30 degrees, just like we did in the example that we just did. Now over here in question number 10, same idea. Okay, the 10 right here has nothing to do with the 5 right here. They're completely independent of each other. But over here you got 2 funny angles, so you're going to have to break this one down, and you're going to have to break this one down separately from one another. Does that make sense? Just a little bit more work, that's all. All right? Let's see what we can do with questions 8, 9, and 10 now. Let's have a look up here. I want to do question number 8, just in case anybody's struggling with these, all right? And let me tell you this. If you are struggling a little bit, that's normal. It's okay, and it's normal. Just because you're struggling a little bit with it doesn't mean you're not going to get this. It is completely normal to struggle a little bit with vector analysis in the beginning. If you are not struggling, then that's wonderful if you're not struggling. Okay? But if you are struggling, it's okay. Lots of people do that go on to end up mastering this stuff. So don't panic about it if you are struggling with it a little bit. All right, question number 8. We see 80 meters, and then we get 40 degrees. The 40 degrees, by the way, would be south of east. What's the first thing you notice with this? It's got a funny angle. And what do we say when we see a funny angle? 5 words. I don't like funny angles. So we do something. We got to get rid of it, right? We do something with it. We take it off to the side and we get rid of it. Here's my 40 meters. I'm just redrawing that 40 meters right there over to the side. Now I'm gonna draw my angle in here is 30 degrees, and then remember to draw your triangle around that. By rights, you should probably draw arrows on the X and the Y, but it's not really a huge deal. Okay, in the end for this thing that we're going to just box off to the side, getting rid of this funny angle, all I want to do is find the magnitude of X and Y. It doesn't really matter which way it's going right now. Now, I had to draw my triangle this way because remember my angle had to be inside the triangle. I couldn't have drawn it like this. This would be wrong because then my angle wouldn't be inside the triangle, right? I had to draw it so that the angle was inside the triangle. Now, some of you try to do this. Some of you on your original diagram just go over like this and say, okay, this is X, this is Y. I'll just do it over here. Don't do that. Okay, don't do that. As the diagrams become more complicated and we get 4, 5, 6 vectors on it, then that just makes it really, really cluttered and we end up making mistakes. Take it off to the side and get rid of it off to the side. All right. Now, we want to find the X component. How much of that 40 meters is X? Well, that's the adjacent side of the triangle, right? We have hypotenuse. Which trig function goes with adjacent and hypotenuse, Victoria? Adjacent and hypotenuse. Good. So let's say cosine 30 degrees is equal to adjacent over hypotenuse. X is often cos, but not always. Sometimes X is Y, if it's the opposite side of the triangle. So X is equal to 40 cosine 30, which I think is 34 point something, isn't it? 34.64. Now let's do the Y component. We're going to say sine 30 is equal to opposite over hypotenuse, or Y over 40. That's going to be, 40 sine 30 degrees. The Y component ends up being equal to 20. We box it off, because that's what we do. We want to make it off to the side, and by boxing it off, it explicitly shows that it's off to the side. Now, let's do our X components and Y components of this. Don't skip any steps. Some of you may want to redraw this a little bit up here, scratch out that 40, and put in 34.64 and 20 meters. You don't actually have to redraw it like that. I'm not going to make you redraw it like that, but some of you may want to do that. Replace the 40 with a 34 and a 20. I'm not going to make you do that, but I am going to make you do this, and I am going to make you do this. What's the X component of the 80, Nate? The X component of the 80. Good. What's the X component of the 40? The X component of the 40. Yeah, Enrique? 34.64. Now, if I didn't have this drawn over here like this, if I didn't redraw that like that, I could have saw that the X component of that was 34. But for some people, it's just easier to draw it in than to not draw it in. Add these up. 80 plus 34.64 gives me 114.64. Now the Y components. What's the Y component of the 80? So what's the Y component of the 80? 0. Good. And what's the Y component of the 40? What is it? Somebody said it? Negative 20, yeah. It's 20 because clearly we calculated that over here, but we make it negative because, well, that 40 was right and down. So that 20 has to be down then, negative. We add those up, we get negative 20. And now let's redraw this. We say 114.64 to the right. And then we say 20 down. Now it's important to draw my arrows on my diagrams. It's critical at this point to draw the arrows on the diagrams. 114 to the right, 20 down, and the resultant vector is drawn from start to finish here. Solve for theta, which is at the start of my vector diagram. R is 114.64 squared plus 20 squared. And theta is the inverse tan function of opposite over adjacent. Opposite is 20, adjacent is 114.64. Let's calculate both of those now. Let's say square root of 114.64 squared plus 20 squared gives me 116. Oh, we got to round this to 2 digits. We got to round this one to 2 digits. So we're going to make it 1.2 times 10 to the 2 meters. But we rounded to 2 digits because of that and that, right? So 116. If it was 114, it would round down to 1.1 times 10 to the 2. But since it's 116, it rounds up to 1.2 times 10 to the 2. Now, theta is the second function tan of 20 over 114.64. Gives me a value of 9.896. We're going to round that to 9.9. 9.9 degrees. Now, what are we going to express that as? 9.9 degrees what of what? Colton, where am I measuring that from?
Southeast.
Good. We're measuring it from the east, but we're going south from the east. So south from east, or just like you said, south of east. Good. 1.2 times 10 to the 2, 9.9 degrees south of east.